Hi everyone. So now we'll talk about multi-scheduler Kubernetes, and to explain that, here is Nurudeen Kamilu.
Hello, everyone. Can you hear me? Okay, good. Okay. Hello. My name is Nurudeen Kamilu. I basically work as a systems engineer, and my day-to-day job has to do with infrastructure management and most especially helping businesses to achieve their objective by cloud native technology to adoption. Today, I'll be talking to you about multi-scheduler Kubernetes, and we'll have a deep dive into, flexible workload orchestration. One thing I want you to have at the back of your mind is that this presentation is different from the typical, scheduler presentation where you expect me to explain, the scheduler algorithm and stuff like that. But instead, we are going to be looking at, Kubernetes scheduling from a very unique perspective. And most especially, we'll be talking about the different myths that we have about, multi-scheduling in Kubernetes. Today, I will be guided by this agenda. The first one has to do with the myth busting, which basically, lets you understand why multi-scheduler is not like, a silver bullet, especially for people that are running, AI workloads or, data jobs. Another one is at the same time we talk about the different scheduling innovations that we have in the open source ecosystem, and then we talk about scheduling from the perspective of governance, and we will end it with key takeaways and challenges that we have when it comes to multi-scheduling in Kubernetes. So let's start with the basics. I don't know if this is not working again. Okay, so the basics basically is scheduler. According to the default definition that we have for Kubernetes scheduling, a scheduler is basically a component of the control plane, right? And its basic job is responsible for making sure that every pod that you basically schedule in the cluster is assigned to a particular node. In making this decision, it goes through different processes, which can be splitted into three. We talk about this filtering, the scoring, and also the binding, right? The filtering is the process whereby you get some information about that particular pod, and based on that, you can be able to select feasible nodes for that, and those feasible nodes are passed into the next stage, which is the scoring, where the scheduler does in some normalization and select the best node, then after which it goes into the binding, where the pod is binded and assigned to a particular node, right? So this can also be well represented when we talk about the scheduling framework, because the scheduling framework is just like a list of extension points that makes it easy for you to customize, different features or access different features of the scheduler through what? Through plugins. Now, let's look at scheduling from a one cluster, or let's look at multi-scheduling from a one scheduler scenario. Here in my diagram, you can see that in this scenario, imagine you have a cluster that is very low scaled. Even if you have different workloads running on it, right? One scheduler can do the job, because it is very similar to having like, a neighborhood cinema, whereby you have one ticketer at the entrance that admits people into the cinema, right? So with one person, and considering the fact that you don't have too much pressure in that environment, that one person is able to admit people before the movie starts at the cinema. Now, if we take it to another perspective, let us look at it from a perspective of where you have now a high-scaled environment. What happens in this scenario? What happens here is the fact that, considering the fact that you have a lot of jobs, or let me say a lot of workload that is to be deployed, the default scheduling queue gets choked. Why? Because the best way I can put it is, behind the scene, you have different workloads that want to be scheduled, right? And all your workloads have different requirements, right? You have your machine learning workloads that want all of the jobs to be scheduled at the same time. You have your critical APIs as well that wants to be scheduled at the same time. And because of that, one scheduler is unable to, to be able to work perfectly under this pressure. Just like you can see in this diagram, where we have one person at the ticketing point of a stadium, where you have a lot of people who want to come in to watch a football match, and that one person is going to be a choking point because of the volume of people that wants to be admitted into the stadium. As we all know as well, the default scheduler works on the basics of FIFO, that is first in, first out, right? So if a pod is to be scheduled, right, the first pod has to go through the whole scheduling process, right? Which means that it needs to filter through, if you have 1,000 nodes in your cluster, it needs to filter through the whole 1,000 nodes. Then from that, it makes the decision, right? Now, imagine it's a Friday where you have like a Black Friday, right? And on Black Friday, you have, a lot of your critical microservices that is requesting for, horizontal scaling, like you want to scale them, right? What happens is the fact that you have machine learning workloads or batch workloads that is being scheduled. At the same time, you have your critical work services that is also requesting for auto scaling. So in this case, what happens is that your critical service will have to wait, or most likely the scheduling queue is going to, or the scheduling backlog is going to fill up over time, right? And this could also cause latency, especially for the critical service that you have. In that case, one thing happens. SLA is not being met, especially when you promise your customers that you give them 99.99% SLA. Now, what is the solution? What comes to everybody's mind is having multi-scheduler, because by having multi-scheduler, every resource or workload that you have in your cluster can be on a separate lane called the correct scheduler and be able to be assigned to a particular node within a short period of time. Do we all agree with that? Does this solve the problem? But in reality, that is not what happened. Why? Because in reality, even though you have multi-scheduler that is being assigned in your cluster, there is still a queue. And why? The queue is because of the fact that behind the scene, we have the same API server, we have the same etcd, and definitely you are also going to have the what? The same congestion. So what does this tell you? It tells you that multiple scheduling should not be looked at. I don't know, this is very slow. Okay. Multiple scheduling should not be looked at from a perspective of job efficiency, or let me say faster deployment, but instead, we should look at it from a perspective of workload governance, workload isolation, and most especially SLA enforcement. So throughout my speech, I want you to have this mindset at the back of your mind so that we can be able to flow into the different stages. Now, we understand that we have different workloads, right? And different workloads have different requirements, right? But for every scheduling, there is what we call the scheduling nightmare, which are the 3 types of workloads that you have in your cluster, or the 3 types of problems that you have in your cluster. The first one is that you have high throughput workloads. For example, your Spark job, your machine learning jobs that want to spin up thousands of pods within a few seconds, right? And these workloads are the kind of ones that basically, fill up your default scheduling queue, right? Especially if you are running Spark workloads. Another one is you have your critical services, your APIs, or let me say your authentication system or your payment system. These are different services that cannot wait for too long in the scheduling queue. Why? Because you have an SLA that is to be met, right? And also, in a case whereby you have different teams that monitor or that shares the same cluster, right? It also had complexity to this. Why? Because you will need to ensure that one particular team is not dominating resources over another team. So the question here is not about whether Kubernetes can schedule, but instead, the question should be about how well your cluster can perform under pressure. So having this in mind, it is important to know that your scheduler is actually the heart of the cluster, because it decides who gets the oxygen in the cluster. And scheduling is not about efficiency. Scheduling is about survival, because for every scheduling decision, it's a life or death scenario for any workload that is running in the cluster. Do you agree? Because when you schedule, the scheduler decides which workloads continue to run, which workloads are queued, or which ones have to wait in the pending state before they are also scheduled. So, just a recap. Remember, we have 3 challenges. Number 1, you have different workloads in the cluster that have different needs, right? We also understand that one scheduler cannot work for everything. And finally, we also want to ensure that we have fairness and isolation for different workloads, or for the different teams or different tenancy that we have in the cluster. Today, it is good that we have the open source system, and the open source ecosystem have a lot of tools that are, that are designed or created for specialized scheduling to help solve this problem. So, in the next few slides, I'm going to be taking a few of these tools, and we can be able to map them to how well we can use them to, to solve some of our problems. Let's start with Volcano. I call Volcano the bash specialist. Why? Volcano is basically designed for HPC workloads, which are basically high computing workloads, and at the same time AI workloads. And Volcano is the first and the only, CNCF project when it comes to batch job scheduling. The interesting thing about Volcano is the fact that it's basically built on to support the native Kubernetes, and it supports different framework, that is, different jobs that you have. For example, you want to run TensorFlow, Spark, and a lot of jobs that you can run in the cluster. Volcano has basically 3 components. We have the Volcano admission controller, we have the Volcano scheduler itself, we also have the Volcano control manager, and finally we have the Volcano Cattle command, which is like a CLI command that you use. Now, interesting thing about Volcano is that for the controller manager is just see it in a similar way, the way you see like the Kubernetes controller manager, right? This basically has other little component managers into them. For example, we talk about the queue controller manager, we talk about the pod group, we talk about the Volcano job manager, which are basically responsible for managing the life cycle of the different custom resources that is provisioned by Volcano. Now, Volcano has a very interesting feature, which is called gang scheduling. Gang scheduling, some people call it schedule all or don't schedule anything at all, right? Because your jobs want to start simultaneously, right? And Volcano helps to achieve this by creating what we call a pod group. A pod group is just a list of pods that have very strong association, right? You can also see it in a simple way like a replica set, but it's different from a replica set because there are conditions that pod group has to fulfill before they can be scheduled. Now, what happens when you submit a Volcano job? When you submit a Volcano job, the Volcano controller watches for the request of that particular job, and based on that, it creates a pod group for you. And from your pod group, then it can create the different pods and adds an annotation of that particular pod group name to the different pods that is basically created. We can also use Volcano for default or let me say native Kubernetes resource deployment. For example, you can use Volcano to schedule a normal Kubernetes deployment or Kubernetes pod. But to do this, you need to manually create the pod group, and on the pod manifest itself, you have to add the annotation of the name of the pod group that the particular deployment belongs to. Now, another thing that Volcano also helps to do is what we call the session scheduling. Session scheduling happens in a way that, let's say for example, in default Kubernetes, right? Kubernetes will take one pod at a time, right? But for Volcano, it's basically a session. That is, it takes all your pod group and look at it that can these pods be what? Can these pods be scheduled at the same time? Because for every job that you have a specification called minimum availability or minimum available. Basically, you're saying that, okay, even though I want 3 replicas, right, I want at least 2 to be scheduled at the same time. So what Volcano does is that it goes and creates a session and confirm that can I schedule 2 jobs or 2 pods at the same time, even if you have a replica of 3. if that condition is not met, then that particular pod or job is not scheduled at all. Then it waits for the next session. So what is the advantage of this? Though there may be latency in your job scheduling, but there is very high throughput when it comes to this. Another feature that Volcanoes provides for us is what we call GPU awareness. Unlike default Kubernetes scheduler that just sees a GPU node as just like a node, right? Instead, Volcano understands the GPU topology. That is, Volcano understands the PCIe bandwidth. It understands the different GPU models, which makes it very intelligent to be able to place, workloads on the right node, or let me say on the right GPU nodes that can be able to help your workload in the cluster. Another thing is that with this feature as well, Volcano prevents GPU fragmentation. GPU fragmentation can be said in such a way that, let's say for example, you have like small jobs that need to be scheduled, right? Instead of your small jobs to just occupy different GPUs randomly, leaving the cluster underutilized, Volcano kinds of package your job efficiently to be able to maximize the GPU you have in your cluster. Finally, Volcano provides what we call multi-cluster scheduling. What is multi-cluster job scheduling? A simple way I can put it. In Kubernetes, or let me say in the open source system, we have what we call Commander. Commander is an open source tool that allows you to be able to schedule different workloads to be able to schedule the workloads on different cluster or in different cloud environments, right? And we all agree that when it comes to large-scale AI training or model training, right, one cluster is not enough, right? So because of that, people try to leverage on using Commander to be able to distribute their AI trainings into different clusters. Now, Volcano has what we call Volcano Global, which is like, a project that basically enhances the feature of Commander. How does it work? It works in such a way that, let's say, for example, you deploy a particular job, that's a Volcano job or a deployment, right? This request is submitted to Commander. Commander has what we call propagation policy. That is, based on the propagation policy of Commander, which is like a custom resource, Commander is able to define where the particular resource is to be scheduled, that is, which cluster should it schedule it. And with that, Commander can create a resource binding to match it to the target or destination cluster. But what happens is that when you submit this job to Commander, and Commander creates that resource binding, Volcano Webhook watches for that resource binding creation and put it in suspension state, right? Once it puts it in suspension state, then the Volcano controller can then go and look into the queue priority, because one thing that this specialized schedulers gives us is when we talk about queue prioritization, right? So this time it's looking at the queue priority on a global level, not just like related to one cluster. And based on that, is able to make a decision that, okay, this particular job can be scheduled. Then it removes the resource binding from the suspension state, which then sends the request back to the scheduler of the Commander, and Commander then can deploy it to the target cluster. Now, I have Apache. Everybody knows about Apache when we're talking about, big data, we're talking about Spark workload and stuff like that. Apache brings in 3 unique features, Apache Unicorn. And one of the unique features is when we talk about, the hierarchical resource queue. It's more like, like a tree structure, which helps you to basically control the resources that you can assign to different tenants in your cluster. That is, making it easy for you to logically map your resource availability and the tenancy to your organization structure. As you can see in this diagram, you can see that, for example, we have that the root queue, and in the root queue, you can see like, different queues that are created for different, teams. For example, data science, marketing, and stuff like that. And with this as well, Commander also creates a feature which has to do with resource fairness and app awareness. That is, a default Kubernetes scheduler, when it wants to schedule a job, for example, right, it just thinks about what is the resource request, right? What is the node affinity and stuff like that. But with Unicorn, Unicorn basically does not just understand the pod itself, but also understand the app and the user that is creating it. That is, for example, if you are submitting 5 pods that belongs to the same Spark application, which is basically what people use Unicorn for, Unicorn understand that, okay, this job is submitted by a user called Nurudeen, right? And Nurudeen has used like 5% or 80% of my quota, and also understanding which team I belong to, understanding whether the team is starving their resource or probably I'm overutilizing the resources that is in my environment. So this is like a very good feature, which means that Unicorn helps solve the problem when it comes to the perspective of multi-tenancy. Now, we have Q. Q, I won't call Q a scheduler, but instead, I will call Q as more of a Kubernetes native system that helps you manage your quota in your cluster, and as well as how your job consumes the different quota that you have. A feature that Q provides for us is what we call the admission-based queuing. What does the admission-based queuing do? Let's say, for example, you submit a job to the Kubernetes API, right? When you submit a job to the Kubernetes API, then the Kubernetes API sends that particular request to the kube scheduler, right? And the kube scheduler can make a decision on, whether to schedule it or not. But Q comes in between this phase. That is, when you submit that particular request to the API server, then Q comes in, that request is sent to Q, and Q has what we call admission checks. Admission checks means that it checks for that particular resource that you want to schedule and confirm if it has enough capacity, or if the cluster has enough capacity to schedule that job. In a case whereby there is no capacity to schedule that particular job, that particular request or that particular job is not even going to get to the scheduler at all. That is, in that case, it is kept in the pending state. Then once enough resources is available, then it can be able to then admit it. That is why we call it admission-based queuing. Q also introduced another thing which is called resource flavor. See resource flavor more like, I won't call it node pool, but what resource flavor basically helps you to do is, it helps you to define the compute resources that you have in your cluster. That is, it makes it easy for you to be able to categorize your resources based on your node, for example, based on the different architecture that they have. For example, you can also do it based on the different GPU types of that particular node, or even based on the pricing model. For example, you can say these nodes are on spot, these ones are, on demand node. So this makes it easy for Q when you create a particular, job and it's being sent to Q. Q can be able to narrow down the nodes in which it's supposed to schedule that particular job on. Then also there is multi-queue. Multi-queue is just the way you see the cluster job scheduling in Volcano, right? With this as well, it's working exactly the same way. That is making it easy for you to be able to distribute your machine learning workload or job across different cluster. But this time it's just like, a single resource called multi-queue. Now, as you can see now, we have talked about different tools, right? And you can see here that these different tools have different resources, right? And different features and capability, which means that one particular scheduler is not enough for everything, because there are always going to be different features that you need in a particular scheduler that is not available in another scheduler. Remember, we started about governance. So governance here now means 3 things, because I said in the beginning of my slide that governance, multi-scheduling has to do with not the efficiency part, but the governance and the isolation of the workloads that you have in your cluster. So if I'm to define governance in this scheduling context, I will say governance has to do with prevention of starvation. That is making sure that one team does not monopolize all the resources in your cluster. It also has to do with the SLA enforcement. That is making sure that your resources are available based on the SLA that is assigned to them. And at the same time, it gives you self-service. Let's take each of them and dig in deep. Let's start with preventing starvation, right? As we can see, with tools like Unicorn, Volcano, and stuff like that, it is pretty easy that you can have different quotas or queues assigned to the different teams in your company, right? making sure that, one particular team or one resources is not over consuming, or let me say, you're making use of all the different resources in the cluster, right? And as you can see, in a case where there is no governance, what happens? Imagine you have a machine learning workload or batch job that is running overnight, right? And in the morning, your main resources are supposed to start up, or there's a high traffic for your critical application, and they don't have, they don't have enough resources to be scheduled on. So the key point here is not about efficiency, but the key point in this prevent starvation is about safety, and is also about what? Governance of your workload. Another thing is the SLA enforcement. Tools like Volcano leverages on what we call the priority class in Kubernetes, right? Priority class basically lets you know that, okay, this particular resource matters more than another resource. For example, I can say I work in a financial industry, and I can say that my payment services matters more than any ML experiment that I'm running, right? So it means that when it comes to the fact that my critical service requires more workloads, it can easily preempt my machine learning experiment and probably pause it, and after that, be able to get the required resources that I need. And at the same time, this also makes it easy for me to have the SLA, or to meet with the SLA that has been what? That has been promised to different, different customers. So in this case, you should be looking into the fact that here your scheduler in the cluster is acting as an SLA enforcer, and this is what we call what? Policy enforcement. It's just like when you are in a flight, right? When you want to board a flight, they tell you that first class people goes in, right? After first class, then second class can go. It's not because the first class people are better, but it's just the law. It is the rule. So similar thing we can try to, place in here with the use of the priority class. Then another thing has to do with self-service. By self-service here, we can basically say that your ability for you to have multiple scheduler in your environment makes it easy for your developers to be able to freely select the particular scheduler that they use, even though there are still going to be a bit of, guardrails to be able to limit the kind of scheduler that they can use, but still they have the resources. And at the same time, let's say, for example, your team needs, to use a particular scheduler. By default, what happens is that they have to make a request to the platform team, right? The platform team then makes a decision on on the scheduler to use. They have to create the Jira ticket. It takes time to, to test it out and make sure it works. But in a case whereby you already have those schedulers running in your cluster, right? Whenever there is a need to make use of a particular scheduler, all the team needs to do is just to add in the name of the scheduler in the job specification or in your port specification, and with that they can be able to now use it. Now, how do you build this governance on a high level? Number one thing is what we call policy enforcement on the namespace. By using tools like Opal Gatekeeper, for example, you can basically define which scheduler are allowed to be used in particular namespaces. On the screen here, you can see a Rego policy that basically says that, okay, this particular scheduler can be used in this particular namespaces, except if it's not in the namespaces that is not permitted to use that particular scheduler. That is the first step. With this being enforced, the second step has to do with the scheduler selection, which is being done by your developer. Where your developer basically just need to put into their port spec or their job spec, the name of the scheduler that they want to use, and finally, we leave the governance to the scheduler itself to enforce the different priorities, the fairness of the jobs, and also the queue to make sure that the rule is being enforced. Now, what are the key takeaways from this presentation? Number one is that scheduling defines performance, not just your job placement. Another thing is that one scheduler does not fit all the different workloads that you have. And finally, multi-scheduler is not about efficiency, but it's about the governance in your cluster. However, there are some challenges that we have. Number one challenge is the fact that, the API server bottleneck, because regardless of whatever scheduler you have in your cluster, right, you still have one API server in the cluster, right? So it still creates a bottleneck, even though people try to solve the problem by creating, different clusters and using tools like, the Commander and the multi-queue. But this also had some cost trade-offs, because the cost of running one cluster is not as easy as, as the cost of running multiple clusters for your AI workloads. Hence, I'm going to conclude by saying that the Kubernetes ecosystem is fast evolving, and by evolving, I mean that there are a lot of schedulers, there are different features that is emerging every day, right? So I want you to go back home, audit your cluster, understand the type of workloads that you have in your cluster, understand the SLA that you care about in your cluster, and also identify the bottleneck where it really lies in your cluster. Because by doing this, you can be able to make the best decision on how to leverage your multiple scheduler Kubernetes, not just for performance, but most importantly, for flexible workload orchestration, for resource fairness, for SLA enforcement. Because in the end, scheduling is not about where your pod run. It's about how your platform performs best to make sure that your business priority is enforced. Thank you very much.
Okay, thank you very much, Nurudeen. So we'll take a few minutes for questions.
So I have a question connected to the myth itself.
Okay.
You never answered how to make it more efficient.
To the myth itself. So
Yeah,
the
how
myth
to make
is
it more
that-
efficient.
that-
with
that's what
the
I'm
same
saying.
congestion, the same ETCD, and the left one was the same. You had the three things.
Congestion.
Right? Yeah,
The same
congestion,
congestion,
ETCD, and API server.
Yeah. So one thing about the myth is that though you can fine-tune the different schedulers that you have in your cluster, right? For example, if you are running Spark load, for example, you can be able to define the limit of concurrent executors that is being created, but it still does not mean that, you are finally solving the problem. You are just limiting it to a particular, particular scheduler that you have. So that is why it is advisable that don't just look at it from the perspective of the efficiency itself, but try to look at it from the perspective of creating flexibility for your developers and also trying to make sure that there is fairness in the resources allocated in cluster.
Okay, so in an event, connecting this with the governance you shown, if we assign each namespace a specific scheduler, will this also increase the efficiency, or is it completely irrelevant to efficiency?
No, it is irrelevant to the efficiency, because by assigning each namespace, though the thing is that every scheduler in your cluster, right, they are sending the same watch request to the API server, right? So regardless of the namespace, they are still looking for that, so it does not affect it. So by limiting the namespaces, it's basically you just limiting the flexibility that the developers have.
Yeah, thank you for the presentation. A quick question, just because if I am using this custom scheduler, what's happening with the default one? Because as I understand, let's say the custom one, default one is looking only for the resources, but the custom one we can decide which, let's say, metric to look to, right? So my question is, like, let's say I want my pods to be scheduled 60% that team and 40% that team. Then what is happening to the default one? Is it like, should we delete it completely, or in practice?
Okay, so your default scheduler is still there, right? But how does the scheduler know which particular workload is assigned to its public? It's through the scheduler name specification. So with that, it can be able to know that, okay, this particular workload is for me, and I can schedule it that can be scheduled by me. So if you have more than one, for example, it's basically working based on that particular scheduler name specification.
More questions?
Yeah, so I wanted to ask, so for example, if we have some namespace and we enable two different schedulers on that namespace, how can we control which scheduler has priority to create some resources?
If you have a namespace does not mean that one scheduler is tied to that particular namespace. You can have more than one scheduler tied to that particular namespace, right? It's just to give flexibility and without narrow. Another way I can give you example is that let's imagine you have a team, for example, right? Let's say machine learning team, right? And they have different namespaces where they have their deployments, right? You can have schedulers that can be defined to those particular teams, saying that 2, 3, 4 schedulers can be used by this particular team. So in summary, it's not about having to limit that resource deployment itself. No, you are not limiting the resource deployment, but basically you are limiting the struggle for resources in the cluster. Does that answer your question?
Yeah, but like, what if two schedulers at the same time want to
Okay, I get the
create
question.
some resources?
Well, okay, two schedulers can definitely not context for the same job. Why? Because of the fact that when you create a resource in Kubernetes, every pod that you create has what we call the resource version, right? So with your resource version, if you create a particular pod and Kubernetes assign it a resource version of 100, right? By the time another scheduler wants to pick it, it's going to notice the Kubernetes is going to reject it because of the resource version has already been implemented by another scheduler, except if a different resource version.
Yeah, but if you have some namespace and, for example, some team wants to create some critical application there, and there is another scheduler in the same namespace which wants to create like 1,000 ML jobs. So how can we like choose which schedule has like priority to create the resources?
So you have two namespaces, right? One team is creating 1,000 jobs, right? And another namespace, right? And they are creating a little jobs. Now, the thing is, there are two different schedulers, right? And the scheduler we only know based on the scheduler name that is called. So even if you have it in many places, if you have like 4 namespaces and they are all calling the same scheduler, it's that scheduler that is going to respond to them, even if the Discord scheduler is in the cluster. Make sense? All right, thank you.
Okay, and I think that's all the time we had. So
Sorry, please. I would like you to please take a survey. It's just like 3 questions to help me, improve on myself. Thank you so much.
thank you very much, Nurudeen. So a quick break, and then we'll have the last session in this room.
Thank you.